in New South Wales for Transurban. He has extensive experience in the development, design and management of transport planning and road design projects. He's a specialist in operational traffic assessment of road networks, motorways, interchanges and ramp metering. He has been responsible for developing the DDI and CFI requirements for a number of intersections in Australia that are currently being assessed for implementation. I'd like to welcome Sam to the stage.
Thanks guys, and before I worked at Transurban I was at Arup, so these guys have stolen a little bit of my thunder, but we've actually worked on a number of projects together, so that's a little bit of a way of background. I'm going to probably dive a little bit deeper than my colleagues did on just DDIs, and actually I've done an assessment as well, looking at some of the impacts that may occur on the mainline merge. So obviously you can look at, as my colleague said, you can look at things in isolation, but good transport planners have to look at the network. And so one of the things I focused on was downstream of a DDI. So really the agenda is what are they? If you don't know what they are, I'll explain a little bit more. Innovation, again touched on, but really the history of innovation in the traffic and transport space. Applying that to conventional interchanges, what we're currently doing, and then look at the operational micro-simulation that I did to understand what may or may not happen downstream of the merge of a motorway as a result of the DDI being installed. So really the context was set previously. We've got an emerging issue that we have urbanisation, which is creating congestion, people are driving, but it also means there's less land available. So, thinking innovatively is, I think, a key requirement. Obviously with congestion comes safety aspects. Obviously most of our sort of unsafe environments are occurring at peak times, not always, and then obviously funding is a important aspect of how we design, and we increasingly have less funding available for building transport solutions. So what is it? This is a DDI that I've flipped from America. It's very confusing if you're driving on the wrong side of the road in America versus Australia. So what I've just done is I've actually just inverted this image. So this is as if a DDI was in Australia. So what does it do? Again, Callan really told the story, but this is a feature of where you basically cross over to the wrong side of the road temporarily if you were driving across the motorway. So quite straightforward, you cross over once and you cross over again. The key aspect to a DDI, as Callan alluded to, is what it does with the right turn. So this is a right turn at a DDI on-ramp. And so you can see you've crossed over once, but your next position, you're actually not crossing over oncoming traffic. And I'll touch on why that has such an impactful benefit that DDIs can bring from safety and also efficiency. So that's, if there's one thing to hang on to, it's how these handle right turns. Very similar to the CFI. I like to think CFIs are a cousin of a DDI. And then the left turn on-ramp movement is exactly the same as what we have today. So it's simply just a left slip in this case. Coming off the motorway, again, the right turn is handled in a different way. You can see that you are temporarily driving on the wrong side of the road, and as Callan alluded to, when they've done surveys of people who have driven through these in the first time, they didn't even know they were on the wrong side of the road. And that's part of the design, the delineation of curves, line marking, and etc. And really that, I think, is an outstanding feature of good planning and good design, that drivers didn't even know they were on the wrong side of the road. And then coming off the motorway on the left turn is exactly what we have today. So there's no change there. So what do you get? Some of the results coming out of the States is you can get up to 40% throughput increase. That just means there is more traffic going through this thing. Crash reduction, Callan alluded to it, but up to 50% in crash reductions. This is when you have retrofit a conventional interchange into a DDI. So this is sort of real metrics coming out of America, they're no longer theory. 30-year life is a projection based on the first one. If you can get 40% increase, these things are going to last a long time, so much so that they might outlast the bridge decks in which they're sitting on. And obviously, if you were to retrofit a conventional diamond interchange into a DDI, you can save on bridge widening and or duplication and get actually better results. So there is a significant cost saving if you were to retrofit. So under that context before about safety, efficiency, cost, you can see why these are starting to tick a few boxes. Innovation in this space is not new. We've done this before, and we are doing it in Australia. It's taken a little bit of time. These things have been around in America since 2009, but we are doing it, and we've done it before. This is a common problem in an intersection. You have movements that are conflicting. And someone, back at the turn of the century, had a great idea. Why don't we just draw a big circle in the middle of the node or the intersection? And you can imagine the flack that that person would have got. But it did something really intrinsically great. It reduced crossing conflicts. You now just have merging conflicts, so crossing conflicts are more unsafe. And it also, in terms of cost compared to signals, maintenance, huge benefit. These are not a one-size-fits-all. You don't put roundabouts everywhere. It's the same with DDIs or CFIs. But it is a tool that we have. And when you unpack and go through the planning process, they generally stack up quite well. They are not for everywhere, neither are roundabouts. And America was really, really late to the game on the roundabout story. I think the Chevy Chase movie, I don't know if you've seen it, but he goes to Paris and he drives around a big roundabout and they didn't know how to do it. They were really late to the game, whereas France, UK and Australia, we picked up pretty early how beneficial roundabouts are compared to, say, a 4 west stop or red lights. But America are now leading the charge, and I think a lot of it has come from that they're an innovative nation. I think Australia struggles a little bit in this space, but also they had those key fundamental constraints, funding, land, etc., etc. So they're really leading the charge, and DDIs are just one of these. Callan's already pointed out the others, so I won't bore you. And innovation in Australia, it's starting to pick up. So I was involved, I was the traffic lead for the Clounger DDI. It's going to be the first DDI built in Australia. And I was also involved in what will be the first CFI built in New South Wales. There's obviously Hoddle Street, and there's a number of planning studies that I'm aware of that are happening in this space. So Australia, we're starting to wake up. In terms of the interchange evolution, we have also innovated in this space. We used to use diamond interchanges traditionally, and I'm trying to show how they take land. So diamond interchange is kind of long and thin, if you like. 2 nodes on each side, which makes it quite inefficient. And we went, okay, well, let's change that. Let's bring everything into a single node, which is why we call it a single point interchange. But you can see the size and the scale of these things. And when they foul up, they're very expensive to fix. Either you have to duplicate the bridge or widen the bridge, and that means while you're building, you can impact the motorway and or the arterial for 2-3 years, depending on how long they take. Obviously very expensive. And if you live near one of these things, you might lose your house. So aside from that, it was a great evolution. The single point is more efficient than a diamond interchanges. They each have their pros and cons. So before really getting into what I've done in the study and then delving deeper into the DDI, I thought it was important to flash up a little bit more of the safety stuff that Callan mentioned. Front Street in Missouri, this is the first DDI that was built, and it was a retrofit conversion of a diamond into a DDI. And the stats that I'm about to show you are 2 years before versus 2 years after. So this is real metric, real safety stats. So what did they find? They found that the injury or fatal rate halved. Okay, so they're not on the premise or the theory, this is real facts. Property damage halved and total crash rate halved. Next door, also near Kansas City, Dorset Street, was near an industrial park. So there was some, well, I don't know if they're going to be able to handle heavy vehicles. Same story. The injury and fatal rate halved, property damage almost halved, and overall, the total crash rate halved. So that's real stuff. And Callan, I love your approach. If there's one reason to do these things, it's because they're safe. I think we're in this industry, the most important thing is a person can get from A to B safely. I mean, I think that's really, on that premise alone, we should be really considering these things. And we are, to be fair. So what did I do? This is a schematic layout of sort of what I did in the model space. Basically have an interchange, I have an on-ramp with a merge. Quite straightforward. And all I did is have that interchange being a conventional versus a DDI. And that is actually, by the way, the first DDI in America. That's what it looked like before, that's what it looked like after, and you'll notice the bridge deck did not have to be widened. Okay, there's a little bit of land take on the terminals, and I can explain that a little bit more if you want, but that's essentially what I did in MicroSim. So what happened to the merge when upstream if it was a conventional versus if it was a DDI? I tested it under different conditions. I stressed the merge, so I tried to recreate a level of service D merge, E merge, and F. And I also looked at the demands as well, looking at different demand patterns, but mainly driven by the right turn. And that's the key kind of thing that I wanted to understand. If I looked at the left turn, well, that's actually not how intersections foul up. Right turns are actually the one you kind of want to look at. Could have looked at many other things, but this is what I limited my assessment to. So before getting into the results, this is now kind of unpacking a little bit more about how a DDI is able to achieve its safety and efficiency gains. As Callan alluded to, at a conventional diamond interchange, there are 10 crossing points. These are the most dangerous. They also require the phasing, as in you're red so that you can go green and vice versa. That's what happens when you have crossing conflict points. You have to stop the traffic. When you convert that to, not that, that's a shame. There we go. When you convert it to a divergent diamond or DDI, the crossing conflict points goes from 10 to 2. You want to hold on to that fact. That's the right turn, that's the other fact that I want you to hold on to if you're going to explain to someone what these things do. That is huge for safety, and I've already shown you what that does and how that translates to the safety benefits. So, because of the many conflict points of the conventional, you require more phasing. And in my case, I had 4 phases, which is the minimum number of phases really at a conventional diamond interchange running 140 seconds. To think about this quite easily, I hope, that means in any 1 hour, there is 74% of the time just given to green movements for all movements. So, because we've got intergreen times, red and amber, that just means that there is 26% where no one is effectively traveling. Because a DDI, unfortunately that's not working, has only 2 conflict points, you can get away with 2 phases. And it's basically split phases. So you run it from the east to the west, and then west to east. 2 phases. And what that enabled me to do, and Callan touched on it as well, is reduce the cycle time. And in this case, I reduced it to 80 seconds, was about where I landed on in the model space. So what did that mean? It meant that I was actually effectively being able to give 6% more green time to all of the movements. Just simple stuff. There's no real trickery here. It just meant that the green time went up. Hence, it's more efficient. So this is the sort of guts of what the assessment was trying to really uncover, is what happens at a right turn at a conventional interchange versus a diamond interchange. I'm trying to give you the driver's eye view of what a conventional right turn looks like and a DDI. So on the left, if we just start on the left, this is the right turn that I'm talking about. In the model space, based on the demands that I had, I was able to give 49 seconds that was relatively optimized. 35% of the hour was green. It meant that a vast majority of the time, it wasn't green, which means a dense build-up of queuing. And in a conventional interchange, that queue sits on a bridge deck. It's very, very inefficiently stored, if you like. The DDI, because of the 2 phases, same thing, right turn, I was able to give more green time to that, even under the reduced cycle time. And this is what I found. What I'm trying to see is, based on the 2 phases, compared to the 4 phases of the conventional interchange, do we smooth that platoon arrival rate? And what you're seeing here in blue versus green, it is slightly smoother. So a couple of call-out points there. If you break the hour up into 15-second intervals, there were 62 times where a conventional had 8 or more vehicles arriving over a 15-second gap. If you do traffic theory, that means less than 2-second headway, that's dense, okay? Versus 32 in the DDI. And similarly, at the bottom end of the spectrum, there were many instances where there was no traffic arriving on the conventional, the DDI had fewer of those, so it's smoother. So how does that translate to the merge from an efficiency and safety point of view? This is the time, if you close your eyes and you imagine in your driver's eye view, when you land on a motorway that is relatively busy, so not this picture, but where it's very, very busy, and you have arrived, let's say in a tight platoon, you've left the right turn, there might be 3 vehicles in front of you, 6 vehicles behind you, and you're all trying to fight for a gap. So does that smoothing ability of a DDI increase safety or efficiency down at the motorway mainline? And microsim can unpick sort of the efficiency, but it's kind of hard to do from safety. So I tried to think of one way to do that. And this is exactly what I was saying. So in the right turn of a dense platoon, you can see there are many vehicles and they're in a tight gap and they're trying to find a gap. White knuckle moment, I guess. And in a DDI, the smoothing rate meant that the gaps were just a little bit bigger. So important to note that the mainline flow was the same. So actually all of the flows in this was the same. So this is really just trying to tease out if there are any benefits. So from a safety point of view, the way I thought about trying to figure out if it was safer was to look at sort of what people were doing in the microsim space in terms of their acceleration at the gore of the merge. And you can see again that the diamond, the conventional diamond, it was quite varied in what they were doing. That you're on the gas, you're on the brakes, what's happening? Versus the DDI, which is quite smooth. And so importantly, the biggest call out is that not only were you accelerating not as hard in the diamond interchange versus the conventional, there were actually times in the model space where people were decelerating. They were on the brakes trying to find a gap. That doesn't sound very safe to me. It'd be great to have some data that these things are evolving and data is going to become available, but microsimulation is really the only tool at the moment separate to having real data that can kind of prove if there's safety benefits. I believe that there will be because of the fundamental reasons of that smoothing arrival rate. So here are some of the gory details. Essentially, I broke it down into what happened at the ramp. So this is speed, again, DDI green, conventional blue. Speeds were up across all of the scenarios on the ramp. As a percentage of benefit of each of the scenarios that I won't really bore you with, it was consistently up. They all showed benefits of the ramp. So if you measure the ramp efficiency based on the travel time, speeds were up, there was an improvement. They had mixed results from the microsimulation space on the mainline. So I don't think it's conclusive one way or the other. Very different scenarios, and this is kind of the vagaries of microsimulation. You know, it's our best shot at replicating reality. It's not perfect, but I don't think there's anything in there that really kind of alluded to me that it was less safe or less efficient. I think it's pretty clear that the ramp improved. Part of the reason why the mainline might not have improved in the same way is that, like network theory, if you free up something, it often has a downstream consequence. By the way, this is why we have ramp metering. The DDI is not a replacement for ramp metering, it's not the right tool. It's just as an outcome, as an output of installing a DDI, was there anything downstream? And I think you can kind of see that, yeah, there were travel time benefits on the ramp, but maybe mixed results at the merge. But overall, as a network, when you took all movements of all vehicles, there was a noticeable increase, and that mainly was found at the DDI. The delay from going 140-second cycle down to 80, plus the two-phase operation, meant that the average delay was significantly lower in the DDI. There was a massive benefit that the DDI brought to the whole network. And that's a very similar story that we get back from the States. So overall, I think the message is that these things are coming. Kind of thank God. It's been a while, but the momentum is really building in Australia. You can see here are the number of them in America and worldwide. Caloundra is going to be the first in Queensland. Like America, Missouri was the first state. All of the other states will follow. That's what's going to happen here. There might be some good reason to not be the first in the world, but really the lessons learned coming from America is these things are working and they're cheap and they're efficient and they're safe. So that's how many are open today. There's obviously a ton in planning and construction. I've been filling this out since 2015, and I've plotted an exponential curve and it's pretty much spot on. So these things are just rapidly increasing worldwide. And you can really see that momentum is really gaining. That's it.